Hello, my name is Samar Alassad. I'm an analytical major working in Dr. Dasgupta's lab. And so the idea of this project is essentially about drinking clean water and in developing countries. When outbreaks such as the case of Yemen, where cholera outbreak was lasted for 6 years with 2 million cases and 3,000 reported deaths, the lack of resources and availability of the laboratories contributed to the rise of the cases and the prolongated time of the outbreak. So the idea to create a portable automated PCR with a gel electrophoresis detection system, so we can test drinking water resources such as dams, wells, and rainwater reservoirs for common pathogens such as E. coli, salmonella, cholera, and typhoid. And so the automated part is so we can minimize contamination and pipetting errors and improve the throughput and productivity of the system. And so essentially the system will comprise of two major parts. The PCR, which is, we use PCR to amplify the DNA, which is shown in figure 1. The process of this is generally 3 steps. The denaturing step, where you split the double DNA to a single DNA strand at a temperature of 94 degrees Celsius, and then annealing step, essentially adding the primers, attaching the primers to the DNA template at a degrees of 55 degrees Celsius to 60 degrees Celsius, and this varies depending on the primer you use. And then the elongating step, essentially making it back to a double stranded DNA. And essentially, this will repeat for about 30 times to amplify millions of copies of DNA. And so the temperature control is very important in PCR, and so the thermoelectric model here is a device that's operated based on the Petler effect, in which electrons will carry energy to transfer heat from the hot to cold junction, which is shown in figure 2 right over here. And so at the cold junction, the heat energy is absorbed by the electrons as they pass from the low energy level in the p-type semiconductor to the higher energy level in the n-type semiconductor. So the power supply will provide the energy to move these electrons through the system. And at the hot junction, the energy is usually expelled to a heat sink as electrons move away from the higher energy level to the lower energy level. And this will comprise of multiple p and n semiconductors. And so in the gel electrophoresis system, it's generally used to separate biological molecules by size. And so usually you can put the DNA in wells inside of this porous gel over here in figure 3. Where the negatively charged DNA is placed at the negative terminal, where when the power supply is turned on, it sets this electrical feed, and then the DNA starts to migrate to this positive terminal over here. And this is the DNA ladder, where it's a marker for wherever the DNA band lands, and it tells you what you have in your what type of DNA sample you have, if it's present or not. And so the system is designed with those principles in mind. And so for the automation part of the PCR, we are using a rotary selector valve where you can have multiple samples or reagent reservoirs, minimizing this cross-contamination. And so in figure 4, it shows this system connections where it uses this microfluidic controller to achieve this multiple sample delivery and switching. Each sample is going to connect to one port of the rotary valve, essentially achieving selective sample delivery, and the system is able to deliver precisely controlled injection volumes. And so for our PCR system here, we are using, shown in figure 5, we're using this aluminum block because of its high thermal conductivity and low heat capacity as a holding for the PCR tubes. And so essentially the heat block usually placed on the cold side of the TE of the thermoelectric model, and the hot side is toward the sink and a fan. And essentially this helps the heat transfer, and so it's and so the top side of the pellet device will absorb the cooling state, lowering the heat block temperature, and the bottom side will ventilate to ventilate the heat absorbed. And so we have also created slits in here so that it can have extra ventilation. And usually there'll be an Arduino. We use an Arduino Uno circuit essentially to control these instructed to increase or decrease the temperature, and power source that is also portable. And over here is our gel electrophoresis. We have proposed of a very compact system with a direct connection to a power supply, so it can eliminate the need for the electrodes and is easy to carry. And in our conclusion here, So the system, we're going to test it for future work because it'll be tested on its ability to complete a minimum of 30 cycles, where each cycle with all the denaturing, annealing, elongating, and heating and cooling should be around 350 seconds. And this is compared to a commercial PCR, and it will be tested on its efficiency and optimization of the temperature stability and the rapid temperature change. Thank you.